Let's just start with one where we're finding the sine of 75 degrees. So you look at the sine of 75 degrees and you're like, well, wait a minute. I'm only familiar with 30, 45, 60, even 90. But if I've got 75 degrees, is there a way for me to connect to a combination of two of those values? If it ends in 5, well, for sure we can use 45 degrees. And if I want to go back and use these addition subtraction formulas, the question becomes, can I take something else that I know, another angle measure I'm familiar with, and add that on to 45 to get to 75? And sure we can. We could add on 30, right? And before you know it, you've got this addition idea, this sum, that involves two angle measures we're very familiar with. And if we got a formula we can use, so if I take the sine of a plus b here, apparently that expands out to all this stuff. I come back over here, I could let a be 45, I could let b be 30, and since this is addition, it doesn't matter. A could be 30, b could be 45. But expanding that out using the formula states take the sine of a, so the sine of 45 degrees. Multiply that to the cosine of b, the cosine of 30 degrees. Add that on, cosine of 45 degrees, right? Because that'd be the cosine of a. And then we conclude that formula with the sine of b, sine of 30 degrees. Once you've got your formula all set up, all expanded out, then we go back to working piece by piece here and evaluating each part. If I have to figure out what the sine of 45 degrees is, I go back to what I know about reference angles, drawing triangles out. So I draw my triangle out, my 45-degree triangle, right? I know this is going to be in the first quadrant, obviously. I set up my sides for a 45 right triangle. And then I ask myself, okay, how do I find the sine of 45 degrees based off of that? Well, sine is opposite over hypotenuse, right? So opposite 45 is 1, hypotenuse is root 2. 1 over root 2 is the sine of 45 degrees. That evaluates this piece. Now we move on to the cosine of 30, which is multiplied to that piece, so we're going to multiply on down here. For the cosine of 30, we're going to set up another right triangle here, another special right triangle here in the first quadrant. Reference angle of 30 degrees. If you set up your connecting sides here, you've got 1 opposite 30, you've got 2 on the hypotenuse, root 3 on the other side. Opposite 30 is 1. For cosine, we're looking at adjacent over hypotenuse. So adjacent would be root 3, right? Hypotenuse would be 2. All right, as we add on the rest of this, seems like there's still a lot of work involved, but we've already set up our triangles now. So if you got to find the cosine of 45 degrees, I can go back to this triangle, say that the adjacent is 1, the hypotenuse is root 2. This is multiplied on this sine of 30. So when I find the sine of 30, well, sine of 30 is going to be opposite over hypotenuse, so it's going to be 1/2. Going back and looking at that triangle. Got all my values in place. Go through, follow my order of operations by multiplying my fractions together. So here I've got 1 times root 3 over root 2 times 2. Since those values are not both underneath the root, you got to keep it separate. You got to write it as 2 root 2. Plus, over here, multiplying across the top, I've got 1. Multiplying across the bottom, I also have 2 root 2. And quite honestly, if you're doing these correctly, you should find you end up with fractions that have common denominators. If they have common denominators, we take one more step. We put everything together as one fraction over that common denominator. And Now on top we would have root 3 plus 1, which are not like terms. We can't put them together due to the radical. Kind of a strange looking answer, but an answer nonetheless. On this one, we're going to look at the cosine of 11 pi over 12. We know that the two angles of measurement that we're always playing with involves degrees and involves radians. Now, if we use the approach that I talked about on the last one, where we're trying to connect the special right triangle measurements like 30, 45, and 60, it might be a good idea if you encounter a radian measure to convert that over to a degree measure. So let's take 11 pi over 12. Let's multiply by what to convert that over? 180 over pi. When you do that conversion, the idea is the pi's will be canceling out, right? And I believe as you multiply through your numerator here, you get, I want to say 1980 all over 12. Or if you divide that out, what do you get? (11 pi over 12) becomes, is it 165? Okay. So you can leave it in terms of radians. It will work. It's just a little easier to convert it over, make it a degree measure. Once you convert it over, I'm going to try to come up with a combination where we're adding or subtracting two values that we're familiar with from our right triangles, our special right triangles, that add up in this case to give us 165. If it ends in 5, like the first example did, starting with 45 would be a good idea. Now, if we're going to get to 165, we obviously need to add on. And we can only add on one other angle measurement if these formulas are going to work, right? Because all the formulas are just A plus B ideas. There's not an extra value in there that we're adding on. So what am I going to add on here? The difference is 120, right? Okay, so as you think about it, 120 may not appear to be one of those special angle measures, but it is a multiple. It's a multiple of 60. When we start setting up right triangles off to the side here to evaluate everything, we should be able to connect to the special right triangle still. All right, taking my formula then for cosine and addition. So I'm going back here to this first slide, right? I'm looking at this third formula here.
Did the tangent ones change?
The tangent ones actually are good.
So just the cosine?
Yeah, just the cosine. So if we're using this cosine formula for addition, breaks up to this form. So expanding all this out, we're going to have the cosine of A, the cosine of 45 degrees, times the cosine of B, the cosine of 120. We're going to subtract the sine of A, the sine of 45, times the sine of B. You got all your pieces that we got to go through and evaluate. Just like we did on the previous example, if I start with this first trig function, cosine of 45 degrees, I draw out my 45 right triangle. I know it's in the first quadrant. I set up its side measures. Cosine being adjacent over hypotenuse, 1 over root 2 would be that value. Now you find after doing enough of these, maybe it's not necessary to draw all these triangles out for the 45s, for the 30s, for the 60s, right? You keep having those same values over and over again. But for something like the cosine of 120, if you draw that out, we know that 120 degrees is going to be in the second quadrant. And we know the reference angle is going to be how much? 60 degrees. So as we build this triangle in the second quadrant, reference angle here is 60. Well, let's see. This side would be the shortest. That'd be 1. Hypotenuse 2. There's root 3. If I'm finding the cosine of 120, cosine still adjacent over hypotenuse, so it's going to be 1 over 2, but you're in the second quadrant. If you remember, you're all students take calculus, right? In the second quadrant, all the sine stuff is positive, but the cosine stuff would be negative, meaning this 1/2 would be negative. We start escaping that first quadrant, we got to keep remembering that, sometimes these values might be negative. As we subtract on, we got the sine of 45 degrees. So opposite over hypotenuse, going back to the 45 right triangle here, that's going to be 1 over root 2. Multiplying on the sine of 120. So back down to this special right triangle sine, we've got opposite root 3 over 2. This 2 is hypotenuse. And this one would be positive, right? Even though we're in the second quadrant, because we're talking about sine, and sine is positive. As you multiply all this stuff out, multiplying it out, first fraction here, we've got -1 across the top. We've got 2 root 2 in the denominator. We're subtracting. We've got 1 times root 3 on the second set of fractions, and then we've got 2 root 2. Got your common denominator, put everything together. We do not have like terms on top, so best we can do is -1 minus root 3 over 2 root 2. All right, looking at these formulas in a slightly different manner, let's take the sine of 20 degrees, cosine of 40 degrees as an expression. Let's add that to the cosine of 20 degrees times the sine of 40 degrees. As one big expression here, one big sum. Directions are still the same, find the exact value. Let's see if we can find a pattern here that might take us back to the addition formula, looks like, maybe for something. And instead of expanding everything out, let's see if we can go back to the beginning. Any of those formulas stand out? First one on that list, which is the addition formula for sine, right? So addition formula for sine, you've got the sine of a plus b, right? And then it follows this general form here. So you're looking for that kind of pattern on these problems, which would take you back to the beginning part, so to speak. The sine of a plus b, which would be sine of 20 degrees plus 40 degrees. We obviously can add those together. We get the sine of 60 degrees. And as long as we keep getting values back here that we can find exact values for using special right triangles, we do that. But if we get to this point and we get something like the sine of 50 degrees, then we're pretty much stuck. Okay, we got to stop at that point. That is our answer. Sine of 60, though, we can figure out. Sine of 60, if I set this up, 30-60 right triangle. Sine being opposite over hypotenuse. So opposite 60, we've got root 3, hypotenuse 2. We've evaluated the expression. All right, if we say that this is the identity we need to verify, following the rules we always have when we're verifying those equations, we pick one side to work with exclusively. Left side would make the most sense because it seems to have the most to work with, right? Understand that cosine is a function, and at no point can I distribute that function through. Okay? There's no distribution here. Instead, the way I need to look at it, based on what we've been talking about in this section, I need to find addition or subtraction formulas that might help me expand this out to evaluate a little bit better. And you'll notice that you've got cosine of an a minus a b value, right? Let's take that subtraction formula for cosine. Let's spell out what we got. We'd have the cosine of a, so the cosine of pi over 2, times the cosine of b, so the cosine of u. Corrected formula now, we're adding on, right? The sine of a, sine of pi over 2, times the sine of b, the sine of u. So really on these, all you're doing, you're applying one addition or subtraction type formula. You're going through, you're evaluating it piece by piece, at least where you can. I know we've got the 4 pieces like we've had before, but notice 2 have variables. We can only evaluate this one and this one. So as we evaluate cosine of pi over 2 and sine of pi over 2, there's no special right triangles we can use here, because pi over 2 is equivalent to 90 degrees, right? If there's no special right triangles we can use, this is where we have to revert back to the unit circle. We have to recall that pi over 2 is up here, and we have to remember that the terminal point associated with pi over 2 is 0, 1. So if I'm finding the cosine of pi over 2, how would I find that knowing that point? Cosine is x. There we go. So cosine of pi over 2 is going to be 0. That means 0 goes in this place. It's 0 times the cosine of u, plus the sine of pi over 2, which would be the y value, right? That would be 1. So I replace sine of pi over 2 with 1. I'm multiplying that to the sine of u. As we multiply everything out, 0 times cosine of u is going to go away, and notice what you're left with. 1 times the sine of u. We verified the identity.